Exponents and logarithms. This is a key topic in the IB Maths Analysis and Approaches course, both in high level and standard level. And I think it's also relevant in the Maths Analysis and Interpretations high level, and I think maybe standard level. But in any case, whether or not it is in your specific course, it is very important to know if you have any interest in mathematics at all, because it makes your life a lot easier, especially exponents. And yeah, in this video, I'll be covering both exponents and logarithms in the course, and I will be starting off with exponents. Now, what we can see here is a little joke with 1x squared here, asking the other, x cubed, do you believe in God? And then the other one saying, well, I do believe in higher powers, which is just a little play on words, because higher powers in exponents means that their power, as you can see here, is higher. Anyhow, I'll get into what all this means. But I'd first like to address why we use exponents and what actually is something called scientific notation. Because I feel like in maths, in school, you learn, especially in maths actually out of most subjects, you learn a lot about content, about what you need to learn for exams, but less about why you're actually learning it, why it's actually important. So I want to start off with this example. So let's just start off with this little problem, which is how many atoms are there in this glass of water? And what we need to know first is the number of molecules in a cubic millimeter of water. If you don't know what that means, that's okay. That's basically just the amount of molecules in just one very little, a very small space, which is a cubic millimeter. And just looking up online using my best friend Google, we can find that there are 33 quintillion 400 quadrillion molecules in a single cubic millimeter of water, which is a very, very big number. But we want to find the amount of water in this glass right here. So what we can then do, let's just try to change our units. So cubic millimeter is tiny, it's just like less than like 1/100th of this cup. So let's try to find cubic centimeters, which is more, which is a better unit to measure the volume of this cup. So let's convert that into cubic centimeters. And in 1 cubic centimeter, there are about 1,000 cubic millimeters. So to find the number of molecules if this is a cubic millimeter, to find the number of molecules in a cubic centimeter, we then go and times that number by 1,000. Now, we don't want just the number of molecules in 1 cubic centimeter, we want it in this glass here. And what we can say is that the volume of this glass is approximately 400 centimeters cubed. And as we can see, let's just make an approximation that this glass is about halfway full. So we can then, to find if this is in 1 cubic centimeter, if it's halfway full, then there are about 200 cubic centimeters. So then we then go ahead and times that again by 200. And finally, we're trying to find the number of atoms, not molecules. And because it's a glass of water, what we can say is that each molecule of water has 3 atoms, because if you take chemistry, you'll know that water is made up of 2 hydrogen atoms and 1 oxygen. So we then times this number again by 3 to find the number of atoms. And the number that this gives us then gives us an approximation for the number of atoms in this water glass. And that is, the exact number is approximately 20 septillion atoms in a glass of water, which is a very huge number. And if we count the number of zeros, if we just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we find out that's actually 25 zeros. Now, imagine if I gave the problem of finding the number of atoms, not just in a glass of water, but in the entire ocean. There's this many zeros in a glass of water. How on earth do we make mathematical, make calculations with the number of atoms in the ocean, or even bigger numbers, like number of, atoms just in our world itself? And the way we do use that is by exponents, very specifically scientific notation. So this huge number can be written as, so 20 septillion can be also written as, instead of really long, we can write it as 2 times 10 to the power of 25, which is, as you can see, a lot shorter and a lot easier. So therefore, instead of saying there are 20 septillion atoms in a glass of water, we're saying there's 2 and then 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and then 25 zeros, we can just say 2 times 10 to the power of 25 atoms in a glass of water, making our life a lot easier. And the reason we do this is because essentially mathematicians are lazy. We don't like making things difficult for ourselves. We don't want to solve problems where we have to use these enormous numbers every time. We want to be able to solve problems using shorter numbers, smaller numbers, because it makes us more accurate, less prone to mistakes, and it makes our life a lot simpler. So, how does this work then? How do exponents actually work? I'm moving now, I'll explain this, moving on to Surds and exponent laws. Now, what does an exponent actually mean? What is a power of something? Now, before we had 2 times 10 to the power of 25, let's just do a little example of 10 to the power of 23. What does that actually mean? What that means is, that basically means we get 10, and we times 10 by itself 23 times. And that's it. So if we had 10 to the power of 3, it would just be 10 times 10 times 10. Now let's do another example with 2 to the power of 11. Hopefully you're getting the gist by now. You probably know this already, but why not just have a little recap? Because just remembering this explanation really helps us later on in the derivation of some equations. But let's do this with 2 to the power of 11. The exponent here is 11. Our base number is 2, so therefore that means that we do 2 times 2 times 2 times 2 times 2 times 2, and then so on until you've times 2 by itself 11 times. And that's it. That is all an exponent essentially means. And therefore, what we can do is, instead of putting that, we can find a general rule. So some number x to the power of, with an exponent of n, means that x multiplies by itself, that number multiplies by itself n times. And that is essentially the basic law of an exponent. Now, let's see, just using this rule, just using this knowledge, if we can start finding some equations. So, the first thing we can find is what happens if we have x to the a, so x, some number with some exponent a, multiplied by some number with some exponent b. And let's go through this together. So, if we have, like I said, some number x with an exponent of a times by some number x with that same number x with a different exponent, what we can say is that, well, let's say x to the a, that's just x multiplied by itself a times, right? And because we're doing x to the a times by x to the b, and remember x to the b, using the same definition, is just x multiplied by itself b times. So therefore, we're left with a situation where we have x multiplied by itself a times, and then times again x multiplied by itself b times. Therefore, let's just do a little example real quick just to show this. if we have 2 to the 3 times by 2 to the 2, we have 2 times 2 times 2. That's what 2 to the 3 is. And then times 2 times 2. And what's noticeable here? Well, that's just 2 times 2 times 2 times 2 times 2. And if you count the number of 2's to find the exponent, we find that we're left with 5 2's, which is 2 to the power of 5. So what that means, and what do we notice? Well, 3 plus 2 is 5. So what that means is, let me just take this all away, that if we have some number x to the a times some number x, that same number x to the b, we get x to the a plus b. So x to the power of the sum of the components. And that's it. That is our first rule. And it's important because this rule you'll end up using a lot. There'll rarely be questions specifically just on this rule, but there will be questions a lot where you have to be able to know this rule and use it, and it is not given to you in your formula booklet. So it's really important that you get practice with exponent questions so that you remember this rule. Now, the next rule is what happens instead if we have x to the a divided by x to the b. Well, it's easier to illustrate this with an example. So, if I took, let's say, 2 to the 5 divided by 2 to the power of 3. Well, remember what 2 to the 5 means? It's 2 times by 2, 5 times. So let's write this out. 2 times 2 times 2 times 2 times 2 divided by 2 times 2 times 2. That's 3 times. And what we can realize is, well, hold on a minute. What happens if you have two numbers, two coefficients or two numbers that are the same in the numerator and denominator? Well, they cancel out. So we can cancel these out, cancel these out, cancel these out. So therefore, the entire numerator has been cancelled out and 3 of the denominator has been cancelled out. And therefore, what does that leave us? That just leaves us with 2 times by 2, which is 2 multiplied by itself twice, therefore 2 to the power of 2. And I'm hoping that you can get the gist here is that if you have x to the a times x to the b, that's equal to the x to the a plus b. And with division, it is the exact opposite. Therefore, if we have x to the a over x to the b, what we can see here, 2 to the 5 divided by 2 to the 3, that's just equal to 2 to the 5 minus 3. Therefore, we just have x to the a minus b. And that is our second rule. And again, it's really important to remember this because you use it a lot and it is not given to you in your formula booklet. So we have a few more laws. But before that, I want to go over a few definitions. So first things first is a number that is squared. Really, a number that is squared is just x squared. Now you don't really need to know this, but I think it's pretty cool to understand why we say that. And we say that because, well, a square is a shape with 4 even sides. All the sides are the same, right? So therefore, let's get some number x. And we draw a square and we set the side length as x. And in any rectangular shape, remember, the area is the height times by its length. But in this case, because the height and the length are the same, it's just x times by x. So therefore, its area is x times x, which is just x squared. Therefore, we say that the area of a square is x squared, where x is the side length. So if we square a number, we turn it from just one side length into a square. And x squared would then be the area of the square with the side length of x. And that's really it. That's why we say that a number is squared is x to the 2. Therefore, now let's define surds. Now, what we can see here is that surds are sort of like in the same way that division and multiplication are sort of opposites to one another, you could say, or subtraction and addition, the sort of opposite sign to an exponent, sort of what undoes the exponent, is a square root. So therefore, what we say, well, if the area of this triangle is given by the side length squared, we find the square root of this area, we just get x. So therefore, if we don't know this and we don't know this, we say that the area of this squared is x squared. Therefore, we can find the side length x just by square rooting it. So therefore, if we do square root of x squared, it's just x. That's it. And that is what a square root is. Then we have a square number. And a square number is really any number that is equal is a number that is equal to any integer squared. So if we take, let's say, 49, we say that 49 is a square number because 49 is given by 7 times 7, or 7 squared. Another example would be 64, because 64 is given by 8 times by 8, which is 8 squared. And 8 is an integer. And really what an integer means is just a whole number. So, for example, 1 is an integer, 2 is an integer, 5 is an integer. Any number that is whole is an integer. But, for example, 1.5 would not be an integer because it is not a whole number. So yeah, that's really just the definition of a square number. And now moving on. Now, we talked about what it means if a number is squared, but what happens if a number is so-called cubed? And I'm hoping that maybe you could guess it. Oh, wrong slide. Oh no. One sec. There you go. So remember that if a number is squared, well, that means that that number squared would be the area of that square with the side length x. So therefore, I'm hoping that you then get if a number then is cubed, therefore, we're just saying that we're trying to find the volume of that cube with all sides of that cube side length that number. So let's draw a cube, and we have our square from before with these two side length x and x. But now a cube is in 3 dimensions. There's also a depth, which means that we have our singular 2-dimensional square with an area of x squared, but we want to find the volume, which means we then need to multiply it by another x. And guess what? X times x squared, given by that, times by x, is just given by x cubed. Therefore, the volume of a cube is given by the side length cubed, which is why we say that when a number cubed is that number times by itself 3 times. Now, same thing with a surd. So just remember this little symbol here is a surd, which means the root. Now, remember I said the square root of a number? Well, what happens if there's some number x was to the power of n? So if we had x to the n is equal to L, and it isn't squared. Well, the nth root of that number, which is given by this surd with a little n on it here, is given by x, is equals x. So if, and yeah, that's really it. I don't think there's much more to say about that. That's just it. So finally, there's surd and not finally, but now we have surd and exponent laws, which are very important. I've already given 2 of them, but these you pretty much need to remember them all because they don't give them to you. But with enough practice, you do remember them. And I think the best way actually to remember an equation is to really understand why that equation works, why some rule works. So what I'm going to do is I'm going to start off trying to derive some of these. So if we have some number x and we put it to the power of a, some number a, and we say that it is equal to L, okay? Some random number L. Now what happens then if we want to make L squared? If we want to square L, well, that means we have to do the same on both sides. So therefore, let's put in a bracket, x to the a, and we're trying to square that whole thing is equal to L squared, right? But what did we say that L was again? Well, we said that L was x to the a. So, therefore, what we can then do is say that that's equal to x to the 2a. Let me give you an example. Sometimes it can be kind of hard to understand and see why just by looking like that. So, let's say we had, I don't know, 2 to the, let's say, no, we'll have 3, we'll do 2 to the power of 3 is equal to, what's 2 times 2 is 4, so multiply that by 2 again, is 8. So 2 to the 3 is 8, right? Now, what happens if we want to square 8? Which is, therefore, we have to do, if we square 8, that we have to do 2 to the 3 squared, which is equal to 8 squared. And what's 2 to the 3? Well, 2 to the 3, remember, we just said is 2 times 2 times 2, right? So we have 2 times 2 times 2, and then that squared. It's equal to 8 squared. But remember what squared just means? It just means whatever's in the bracket squared times by itself. So it's equal to 2 times 2 times 2, and then times 2 times 2 times 2. What do you notice? Well, how many 2's are there? There's 6 2's. So therefore, we just say that's equal 2 to the 6. And guess what? 2 to the 3, 2. What's 3 times 2? 6. So therefore, 2 to the 6. And what we can see is that when we have an exponent and then we have another exponent in a bracket outside, what we do is then multiply the 2 exponents. And that makes our life a lot easier. I'll try to go through one more quick way of being able to understand this, is if we have x to the power of a, and then we want to square. Oh no, I'm so sorry. Okay, right. Sorry about that. So if we have x to the power of a, and we want to square that, therefore we would have x to the a squared, right? And what does that mean? That basically means we're doing x to the a times by x to the a. And remember our other rule, if we have x to the a times by x to the b, so x with some exponent is just equal to x to the a plus b. Well, therefore we can say that that is equal to x to the a plus a. And what's x to the a plus a? Well, that's just the same as saying x to the 2a. And what we can see, again, is just multiplied by itself. And there we go. So yeah, that's another rule that's really important to remember with exponents, because it's not given to you in your data booklet, and it's quite important. So let's just take this away, and then we have another few rules to get through. I'll try to be quicker about them. Right. So, next rule. What happens if we have x to the power of a negative number? So, we have this, and we have x, let's say for now, to the power of negative 1. What does that mean? Well, what's negative 1? That's just 0 minus 1, right? So we can just write that as x to the power of 0 minus 1. And remember the previous law that I gave with division? That x to the a over x to the b is equal to x to the a minus b, right? Therefore, what we can say is that that is equal to x to the 0 divided by x to the 1. And one really important thing to remember that I should also have here is that any number to the power of 0 is always equal to 1. Even 0 to the power of 0. And there's a whole proof for that, which I'm not going to get into now because you really don't need to know it. But that is another really important rule. So, well, therefore, if we have x to the 0 is 1, therefore we have 1 over x to the 1. And if we have an exponent of 1, therefore we can just take away the exponent. Because if we have an exponent which is 2, that means that we times that number by itself twice. For example, x times x. But if it's just one exponent, it's just x. So therefore, we can just say that it's equal to 1 over x. So x to the negative 1 is 1 over x. And that is a really important rule because it allows us to find the exponents of negative numbers. So let's say this time that we wanted to find x to the, I'll take this away for now, x to the power of negative 3. So negative n, actually. I'll say some random number instead of just 1. So if we have x to the power of negative n, well, we just do the same thing, right? So we have x to the 0 minus n, which is equal to x to the 0 over x to the n. And then just the same rules, you just do 1 over x to the n. So really, x to the negative 1 is equal to 1 over x. So, and the other two things to remember are x to the 0 is equal to 1, and x to the negative n is equal to 1 over x to the n, where x is any number, remember that. Right, moving on. Few more. Now, we have surd laws. We're finished with exponent laws. Now we want surd laws. And remember, surds written as like that, which is sort of like the opposite of square roots. Opposite of exponents. So, let's go into our first law. Let's say we have the square root of a times by b squared. Well, remember that if we have the square root of something squared, that's just ab, right? So we'll just write that as ab. Now, we also know that a is equal to square root of a squared, which is just square root of a times by the square root of a. And the same for b. b is equal to square root of b times the square root of b. So, therefore, what we can do is say that that is equal to the square root of a times the square root of a times by square root of b times by the square root of b. And if you just rearrange that, you can find that that is equal to the square root of a times by the square root of b times by the square root of a times by the square root of b, because they're all multiplied by each other. And because this is the same as this, therefore we can just write that that is equal to the square root of a times the square root of b, all squared. Now we have an equation with, on the left-hand side, we have a square root squared, and on the right-hand side, we have something squared. So if we take the square root of both sides, therefore, we can find that the square root of AB is given by square root of A times by the square root of B. And that is our first Surd law. And it's really important to remember because it appears a lot in exams in terms of not normally on a question on its own, but it does appear in terms of other questions. Now the next one, I'm just going to take all this away, is, well, we now know that the square root of a times the square root of b is equal to the square root of a times b. Therefore, what happens if we do same thing, but with the square root of a over b? So let's start again. We'll say the square root of a over b, and then square that is just a divided by b. And same thing again, we can just say a is the square root of a times the square root of a, so we write root a times root a over root b times by root b. What we realize is, and that's just root a over root b times by root a over root b. So therefore we can just say that's equal to the square root of a over the square root of b, all squared. And then guess what? Look, again, we have a square on both sides. So if we just square root both sides again, we find that the square root of a divided by square root of b is equal to square root of a over square root of b. And there we go. We have our next rule. And again, this appears a lot, and it's good to remember. Right, let's move on. There's one more Surd law that's really good to know because it helps us a lot. And this one's slightly different, and you'll see why. Because let's take x to the power, let's say that some number x is given by some number a to the power of n. Now, remember therefore that means that the nth root of x is equal to a, right? So just remember that for now. We'll put that up here. But let's say instead of just trying to say that, what happens if we try to make the exponent of a just 1? So we're trying to make it a. The way we can do that is, well, how do you, can you times some number n to make 1? You can times it by 1 over n. So therefore, what we can say is x to the power of 1 over n is equal to a to the n divided by n, because we have a to the n times by 1 over n. It's just a to the n over n from our previous rules, remember? So anything divided by itself is just 1, so therefore what we can say is a is equal to x to the a to the 1, because n over n is 1, is equal to x to the power of 1 over n. But wait a minute, didn't we say that a was equal to the nth root of x? Well, we did, and that is also correct. Therefore, what we can say is that the nth root of x, and that works with square roots, that works with any root, is equal to x to the power of 1 over n. And there we go. That is our last Surd rule. And it is important to remember as well. You don't need to understand the derivation, even though I think knowing the derivation helps you remember them. But it is really important to do lots of practice with these. Now, let's move on. In your exams, they will sometimes ask you to give, especially in your paper ones, which are your no calculator papers, they'll ask you to sometimes to give an answer in its simplest form. If you get an answer in form of a surd, that means you need to try to figure out how to simplify that surd. So how to simplify that square root, or that nth root. And really, when you try to simplify a surd in its simplest form means that the number in the surd is the smallest possible integer, the smallest possible whole number. And then let's just go over some examples to demonstrate what that means. So, if we have the square root of 92, well, we know that 92, what's 92 equal to? Well, we can just divide it by 2. So therefore we can say that that is equal to 46 times by 2. And 46 can yet again be divided by 2. So we can say that that is the square root of 23 times by 2 times 2, which is 4. So square root of 23 times 4. Now, we know that 23 is prime, right? So this can't be simplified anymore. But 4, however, can be. And remember our previous law? That means our previous law, which is the square root of a times square root of b, is equal to the square root of a times b, right? And here we have a is 23 and b is 4. So therefore we can just separate it into square root of 2. Let me just take this away because I won't need it. Square root of 23 times by the square root of 4. What's the square root of 4? Well, the square root of 4 is very simply just 2, because if you do 2 squared, or 2 times 2 is 4. Therefore, our simplified version of this is given by 2 root 23. Just put a little arrow. Simplified. Great. Now let's do one more example just to make sure that we're good with this. So if we do square root of 54, well, what is 54? 54 is 9 times 6. So you can put it's equal to the square root of 9 times by 6. Again, we can just say that this is the square root of 9 times the square root of 6. And what is the square root of 9? Very easily is 3. So we put 3. And 6, well, 6 isn't, like I said previously, remember, a square number, which means 6 can't be square rooted to make an integer or a whole number. Therefore, we leave 6 as it is, and we say 6. So there you go. So we have our 2 simplifications. So square root of 54 is equal to the square root of 3 times root 6. And that's it. That is simplifying surds. Now, let's move on to an exam question. Kind of question that would appear in your IB exams. And this is a whole 5 marks. Right, so let's start off. We have 27, basically we're just trying to find the values of x. 27 to the power of x plus 2 is equal to 1 over 9 to the power of 2x plus 4. I'm trying to remember our rules here. Remember 1 over 9. What can you do with 1 over 9? Well, that's just remember that x to the power of negative 1 is just the same as 1 over x, right? So therefore 1 over 9, we can write it as equal to 9 to the negative 1. Put that in brackets, 2x plus 4. What's another thing that we can notice? Well, both 24 and 9 are multiples of 3, right? So let's see if we can do anything with that. What's 27? Well, 27 is 9 times by 3. Great, but 9 is also 3 times 3. So therefore we can tell, 27 is equal to 3 times 3 times 3, which is just the same as 3 to the power of 3, or 3 cubed. And 9, like I just said, here is 3 squared. So what we can do is then find 27, well, that's 3 cubed, so we can just put 3 to the power of 3, all that to the power of x plus 2 is equal to 9 to the negative 1. Well, that 9 is 3 squared, so we can just say 3 to the power of negative 2, because if you have 3 squared times by negative 1, 3 to the power of 2 to the power of negative 1, that's equal to 3 to the power of negative 2. So therefore, 3 to the power of negative 2, and then again to the power of x plus 4. And now, what's great is that we have bases of 3 on both sides. And then we can just use our rule to find that 3 times by x plus 2, which is 3x plus 6. So 3 to the power of 3x plus 6 is equal to, what's negative 2 times 2 is negative 4. So we have 3 to the power of negative 4. Oh no, it just did that again. Oh, so sorry. I think we were here. 3 to the power of, let me just write it out real quick again. 27 to the power of x plus 2 is equal to, I think it was 3 to the negative 2 to the power of 2x plus 4. Therefore, we can say that 3 to the 3x plus 6 is equal to 3 to the negative 2 times 2 is negative 4x plus, and then what's 2 times 4 is 8, so sorry, not plus, negative 8. And what we can notice here is that the bases, these numbers here are the same. So we have 3 to the power of something a. So let's say 3x plus 6 is a, so 3 to the power of a is equal to 3 to the power of b. What does that mean? Well, that means that a must be equal to b, right? Because if you times 3 by the same number of times, you're going to get the same number. So therefore, what we can say is 3x plus 6 is equal to negative 4x minus 8. And then we can just do some basic algebra. We can therefore just say that 3x plus 4x, which is 7x, is equal to what is negative 8, negative 6, that is minus 14. Just doing some algebra. Therefore, we can just rearrange that and say that x is equal to minus 14 divided by 7. And what's 14 over 7 is just negative 2. For x is equal to negative 2. And there's our answer. And when you do this on your own, it goes a lot quicker once you've had enough practice. I've just gone over every step just to make sure that everything is understandable to you guys. Now, we've covered everything in exponents. Let's move on to logarithms. And this is a little joke. And I'm hoping that once we've covered logs, you'll be able to go back to this and be able to understand why this works. I might go back to it myself. So Again, I think it's really important to go over what logarithms are and try to introduce it in a good context. So let's try to introduce logarithms with this question. I want you to really think about this question as I talk about it. So the earthquake in Japan on the 11th of March 2011 released so much energy it caused the entirety of Japan to tremble and a 10-meter tsunami to hit its northeastern coast. So you can imagine the amount of energy it takes to make an entire country tremble. And so therefore, we can say that this, if it lets me, there you go. This energy was about 2 times 10 to the 25 joules of energy. Now remember, 2 times 10 to the 25 is a very, very large number. And that's actually the same as the number, I don't know if that is just coincidence, but that is the same amount of atoms that we calculated to be inside of a glass of water. So 2 times 10 to the 25, that seems to be appearing a lot. Anyhow, joules is just the unit for energy that we use in physics. If you take physics, you'll understand that. Anyhow, so we have, that's about 2 times 10 to the 25 joules of energy. Given that the amount of energy released in an earthquake, so we're calling that E, in relation to its magnitude on the Richter scale, M, so the magnitude of an earthquake is given in on a certain scale called the Richter scale. It's given by a number. And given that the amount of energy based off of its magnitude on the Richter scale is given by this equation, what was the magnitude of the 2011 earthquake? So we're given E, amount of energy, that's 2 times 10 to the 25, seemingly some magical number because it keeps appearing. And therefore, what we can just do, first things first, is to then substitute it into this equation. So 2 times 10 to the 25 is equal to 10 to the 11.8 plus 1.5 m. But we're trying to find the magnitude of this earthquake. And the magnitude is in the exponent. How do we find this m in the exponent? And the way we do that is using logarithms. Now, before I answer this, let's quickly go over what logarithms are so that maybe you can have a go at answering this for yourself. So what are logarithms? So if we have some number a, and then we put it to the power of some other number x, we say that that's equal to b. If we want to try to solve for x, if we want to solve for x, we want to find the value of x, how do we do that? If we want to find the value of the exponent, how do we do that? Well, we can find x through logarithms. So therefore, if a to the power of x is equal to b, we can say that log base a, so we call this number the base of the log, and we say that that's equal to b, x, and that's it. Oh, maybe I should get rid of that. And you don't even need to remember this. They give it to you in your formula booklet, though you really should try to remember it, but it will come with practice. And because remembering it makes your life a lot easier, as you'll see later, some of the questions can be quite difficult. So yeah, now using that, let's see, using this right here, let's see if we can try to find the answer to our previous question. So we have 2 times 10 to the 25 is equal to 11.8 plus 1.5 m, right? And we know that a to the x is equal to b, therefore log a of b is equal to x. So therefore, we can try to find this. Let's substitute this into this equation. We can say, therefore, that a is equal to 10, because we have 10 to the power of what we're trying to find. And b is 2 times 10 to the 25, because we say that a to the x is equal to b. Therefore, what we can say is that 11.8 plus 1.5m is equal to log base 10, so remember a, of 2 times 10 to the 25. Because this is the power, this represents x. And when we rearrange that to solve for m, we find that m is given by this, and the final answer is approximately 9. So therefore the earthquake had a really high magnitude of about 9 on the Richter scale. And the way I was able to do this was obviously not my head. I used a calculator. And I think that most of you are probably using a TI Nspire Texas Instrument calculator. And if you are, I'll just show you real quick how to find the log function on your calculator. If you don't have the same calculator, then feel free to skip. I'm sure it's going to maybe be something similar, but I'm not too sure, so I can't advise you on that. So, on your TI Nspire calculator, to get the log, to be able to put this equation into your calculator, what you do is you first of all press Control, and then you press this button right here, right below where it says log. And then that won't put, because you've pressed Control, that will just put x to the 10. So you hold Control and press this button right here. And that's it. Now, like with exponents, logarithms also have some rules. But the nice thing about the log rules is that they're given to you on your formula booklet. So the first one is the product rule. But again, it's really important to be able to remember them so that you can apply them really quickly in your exam. And to remember them, I'm going to go over their derivations because that often really helps with remembering different rules, logs, different rules, because you can actually understand them. And by the way, really feel free to go along and try to write along with me as you're trying to derive it yourself, because you'll see it's a lot easier to understand something if you're trying to do it yourself than just by watching it. So let's start off with this. We have let's say we have some number a to the power of b, and then we multiply that by a to the power of c. Remember our rule from exponents, we say that that's a to the power of b plus c. Now, let's now say that a to the power of b, just this, is equal to x. So let's say a to the b is equal to x. And now let's say that just this is equal to y. So a to the c is equal to y. And therefore, then we can use this, using our log, a definition of a log, we can therefore say that b is equal to log base a of x, and c is equal to log base a of y. And now using this, we can find this rule, because we can therefore say is a to the b times a to the c is just x times y, right? So therefore we can say that x times y is equal to a to the power of b plus c. Now remember, we've also defined b and c being log base a of x and log base a of y. So we can say that x times y is a to the log base a of x plus log base a of y. What can we do with that now? Well, let's try to make this equation x times y is equal a to the power of log base a times x plus log base a of y. And let's try to put this on its own on one side. Well, we can just then again use identity of what a log is. Therefore, what we can say is log base, and therefore we can say that this is equal to log base a of xy, right? So therefore we do log base a of xy is equal to log base a of x plus log a of y. Sorry, that's a bit tight. And that's our identity. And again, this is given to you in your formula booklet, so you don't really need to fully memorize this. But it's a cool derivation, and it allows us to do a lot. Now, let's move on to our next one, the quotient rule. And really, this is the logarithmic quotient rule. And this is really very much the same thing as our previous one, because we can just do a to the power, so remember a to the power of b over a to the power of c is equal to a to the power of b minus c, right? So therefore what we can say is, remember what we can do is we can say a to the b is x, and we can say a to the c is y. Ooh, that is not meaning to be fancy, right? There you go. And therefore we can say that b is equal to log base a of x, and c is equal to log base a of y. You can put that all in a bracket. And well, what we can do now is then, well, like we did previously, we can say a to the power of b is x and a to the power of c is y. Therefore, we can just say that x divided by y is equal to a to the b minus c. And remember, b and c, b is log base a of x and log c is log base a of y. So therefore, we can just say that's a to the power of log base a of x minus log base a of y. Then again, we just use our definition of a log. And then we can find that, therefore, log base a of x divided by y is equal to log base a of x minus log base a of y. And that is the log quotient rule. Again, it's given to you on your, that should say formula booklet, sorry, that formula booklet. But remember, do try to remember what it is, because it really does help you. Now, second to last one for logs is the power rule. And this one you use very frequently in any exam paper, any exam question on your on the IB exams that use logs. And the derivation is pretty simple. Because we start off with, let's say a to the power of b is equal to x. Therefore, we can say that b is equal to log base a of x, right? Therefore, what we can do, if we do x to the power of some number m, well, remember what x is. X is a to the power of b, and we can use our previous rules. We can say that that's equal to a to the power of bm, right? So therefore, now let's try to find the log of that. Let's try to find logs. So what we can then say, therefore, is that, remember what I defined b as? B I defined as log base a of x. Therefore, what I can do, that's equal to a to the power of log base a of x times by m. And now again, let's try to make this exponent on its own. Let's try to find this equation on its own and not as an exponent. Therefore, we just make it in terms of logs. We can say that log base a, because here it's a to the power of, log base a of x to the power of m, because here it's equal to x to the m. therefore is equal to log base a of x times by m. And that is the logarithmic power rule. And I don't know if you can tell, but this is the rule where I got the joke at the beginning from. If I quickly of this section right here, because remember, if we have m times by log of x is equal to log of x to the power of m, which is the rule we just did. Therefore, this emoji times by log of this smiley face is equal to that same smiley face with a little teardrop on the side. Just thought that was a little funny thing to maybe help you remember this rule. The change of base law in logs is probably the most useful logarithmic law, because it allows us to take one log expression and we can actually find an expression with logs again, but with different bases, and that base can be any base we want. And the derivation is pretty simple, and you'll see later when I do an exam question how useful this is. But I'm going to start off. So let's say let's take log base a of x, and we set that equal to y. Therefore, we can say that a to the power of y is equal to x, because that's the definition of a log. Now let's introduce our new base. We'll say that log base b, some other number b that we can choose, of a to the power of y is equal to, and what's a to the power of y? It's just x, right? So we can just say log base b of x. Now, what can we do to that? Well, what we can say is that, remember our other rule, which is that our log power rule, which says that log b times by log a to the power a is equal to log of a to the b. That's our power rule, right? So therefore, with that, what we can deduce is that therefore y times by log of b times by a is equal to log of b x. And what that lets us do is then we can then do, well, therefore y is equal to, just rearranging, log base b of x divided by log base b of a. Up here, what did we say y was equal to? Well, we said y was equal to log base a of x. So therefore, we can say that log base a of x is equal to log base b of x divided by log base b of a. And that is the change of base law. And that's given to you on your data booklet. Now, before we finish with logarithms, there's one last thing to know, which is the natural logarithm. The natural logarithm, it just presented everything. Whoops. Oh well. So we have a constant called e. We have a constant given e, sort of like how that is pi. We say e is a natural number, or Euler's number. There you go. and it is given by 2.718281828459045, and it continues going on. And just like the number, it would be irrational for me to keep listing out the numbers. But yeah, basically E is irrational, just like pi, which means that this goes on endlessly and randomly. There is no pattern, and it continues on endlessly and randomly. And a logarithm with a base number of e, so a logarithm with a base number, so remember the base number is this. Therefore, a logarithm with a base number of e is called a natural logarithm. And instead of writing log base of e, natural logarithm, we just write as ln. And I can go over what e actually means, what that actually means, but that's more relevant to the calculus part. That's more relevant to the calculus topic. So you'll learn about that later in calculus. But really, all you need to know for exponents and logarithms is that a log with a base of e is just called ln. And that's it. Now, final thing is let's do an exam question. Now, this is a rather harder one, but again, your exams are going to be rather hard, and it's a full 5 marks. So we can just go through it, but you'll see when you actually go through step by step, if you remember the rules well, which most of them are given to you already, it's not really that hard. So let's start off with, we have a plus b, and we're trying to find the integer values of a and b, where an integer, remember, is a whole number. So we're trying to find an integer values for a and b when a plus b times log base 4 of 7 plus 60 log base 8 of 14 is equal to 0. Right, what is the first thing we can see? First thing we can see is that the log bases are different, and that makes our life a lot harder. So we want to make both of them the same base. And remember, we can just use the change of base rule. So therefore, to make it into any common base we want. So just for simplicity, I'm going to use ln. So therefore, we can say that log base 4 of 7 is equal to ln of 7 divided by ln 4. Feel free to just go back and look at the change of base rule, but essentially that's it. And therefore we can do log base 8 14 is equal to ln of 14 divided by ln of 8. And that's it. Now we can substitute these into our equation. Therefore, all of our logs have a common base of ln. So, therefore, we can say that that is equal to a plus b times by ln of 7 divided by ln 4 plus 60 times by ln of 14 divided by ln of 8 is equal to 0. And what's one thing we can do? Well, what is 4? 4 is 2 to the power of 2, right? So therefore, ln of 4 is equal to ln of 2 to the power of 2. And remember our power rule, we can just therefore say that's equal to 2 times by ln of 2. So therefore, we can then make this denominator 2 times by ln 2. With 8, well, what's 4 times 2 again? Is 8, right? So 8 is 2 to the power of 3. So therefore, we can say ln of 8 is equal to ln of 2 to the power of 3, which is equal to 3 times by ln 2. So therefore, we can rewrite this saying that that is equal to a plus b ln of 7 divided by, remember what ln 4 was, it was 2 times by ln of 2. And then the same thing, 60 plus 60 ln of 14 divided by 3 times by ln of 2 is equal to 0. I'm going to move on to the next page in a minute because it seems that every time I keep writing down on the page, it turns off my thing. So, but yeah, essentially that's what we have. And so I'm going to write that out on the next page. So we have a plus b ln 7 over 2 ln 2. So we have a plus b ln 7 over 2 ln 2 plus 60 ln of 14 divided by 3 ln 2 is equal to 0. And what's one thing that we have now is we want to get rid of these fractions because these fractions are big, bulky, and annoying, right? So what's one thing we can do? Well, if we times everything by ln 2, what happens? Well, we get a ln 2 plus, guess what? We have b over 2, and then ln 2 and ln 2 cancel out, ln 7 plus 60 over 3 is 20, so therefore we just have 20 ln 14. That is not a very good 4. Write that again. 0. This is looking a lot simpler now. So therefore what we can now do is, well, we want everything in our lns to be the same, right? That makes things easy for us. Because again, mathematicians are lazy. And what is ln 14? Well, that's the same as saying plus 20 ln 2 times by 7, right? And guess what? We can then just use the product rule, the ln product rule, by saying therefore that's equal to 20 times by ln of 2 plus 20 times by ln of 7. And that makes us lives really easy because now everything is in terms of ln 2 and ln 7. And also it means that we can now equate coefficients because we see we have our ln 7 there and ln 7 there, and then we have a ln 2 here and a ln 2 here. So therefore what we can do is we can take ln 2 and we just equate coefficients, which means we can do ln 2 times by a plus 20, because if you do ln 2 times a and then plus ln 2 times 20, that's ln 2 times a plus ln 2 times 20, right? So therefore we equate coefficients. We just do plus ln 7, and then guess what? We have b over 2 and 20. Therefore we have b over 2 plus 20. All that is equal to 0. Now we're in a situation where we have ln 2 times something plus ln 7 times something is equal to 0. And one thing that we know is that that ln 2 is not negative, right? Because e to the power of something, a positive number to the power of something, is not going to be 2, right? It's going to e to the power of a negative number must be, ignore that, that's wrong. Anyhow, what we need to then find, therefore, we have ln 2 times by a plus 20, right? and we have ln 7 times by b over 2 plus 20, which means that in order for these two to be 0, we have to say that this must be equal to 0, and this must be equal to 0, because ln 2 times by 0 is 0, plus ln 7 times by 0 is also 0, and 0 plus 0 is 0, obviously. So therefore, the first solution for A, which is a solution for A, we can say, therefore, A plus 20 is equal to 0. Therefore, A is going to be equal to negative 20. That is our first solution for A. And now our solution for B, we can say that B over 2 plus 20 is equal to 0. Therefore, B plus 40 is going to be 0. Therefore, B is going to be equal to negative 40. And we have our two solutions. And that is that problem. A is negative 20 and B is negative 40. Finally, let's just do a little recap, because that is everything in logs and exponents. Now, these are the exponent equations as well as just this log one that you do need to remember because it isn't given to you on your formula booklet. And these ones are the log laws that are all given to you in your formula booklet. But again, like I just did with this problem, you can see it's a lot easier if you know these laws off by heart. So remember, try to go over these ones and try to do lots and lots of practice with them because especially with exponents and logs, these are really important in your exams. And to be honest, these appear so much in practice questions that if you do enough practice, you will end up remembering these. And really, if you look at the derivations, they just make sense. So there you go. Thank you very much for watching, and I hope you watch some of my other videos if you like this one. If not, there are plenty of other good channels. I think I've linked a few in my description that do very good maths explanations and physics explanations if that's what you're doing. Anyhow, thank you very much for watching.